A way to quantify the evolution towards equilibrium is using the quotient Q. The Q has the same expression as K, it's just that you can apply Q at any point during the reaction, not necessarily in equilibrium. For the expression of K, you only plug in the concentrations in equilibrium. If it's not in equilibrium, that ratio of concentrations is called Q. And how does Q change? Well, let's give you an example. Imagine this reaction when N2O4 decomposes into two molecules of NO2. The equilibrium constant for this reaction is NO2 squared divided by N2O4. So at the beginning, you have, and initially, you will have zero products. That means that Q at the beginning, being products over reactants, you have 0 over whatever concentration of products you have. Q is 0. Q will change, the ratio of concentrations will change until it stops and Q is equal to K. So this is why we say that when Q is lower than K, the reaction needs to evolve towards products. On the other hand, if initially you only have, you start with only products and have 0, whatever quantity you have, let's call it A, and you have only products, then you will have A over 0. This is infinite. Okay, so this means that when Q is larger than K, there's not going to be a K larger than infinite, so when Q is larger than K, the reaction needs to evolve towards reactants. So here you have a strategy to assess if a reaction has to go either towards products or towards or towards reactants in order to achieve equilibrium. And that can be qualitative or quantitative, but notice that until you reach equilibrium, Q will not be equal to K. In this case, we have started with zero reactants. That means that at this point, Q is 0. And Q increases until Q is equal to K, and at that point, you have reached the equilibrium. Okay, so if you were to plot, in this case, Q over time, because you start only from reactants, Q starts being 0 until it reaches the value of K. Okay, let's give you an example of a numerical example so that you can see how useful this can be. Imagine that you have in a container, you add these many moles of sulfur dioxide, these many moles of oxygen, these many moles of sulfur trioxide, and they react according to this reaction. The volume of the container is 2.7 liters, and it's asking you to calculate the quotient Q, and it will tell you, what is it going to go to the right or to the left. First, let's calculate Q. Q will have the same expression as the equilibrium constant, that is concentration of products over concentration of reactants. And we can just plug in the concentrations. We'll have to divide by the volume. Okay, so we have 5.45 divided by 2.7 liters. Of course, the concentration is in molarity. Oxygen, we have 6.81 over 2.7. Let's not forget the exponents. And for sulfur dioxide, you have 4.99 divided by 2.7 again, and the exponent is 2. Notice that 2.7 doesn't cancel out. If typically you can directly work with moles if you have the same number of molecules in the numerator and denominator. In this case, you have 3 times 2.7 in the as reactants and 2 times 2.7. So you will need to plug this into a calculator, and this gives a number. And this tells you that the equilibrium constant is this value, is 3.7 times 10 to the 3. Okay. If Q, so I'm not gonna calculate it, you can do it at home with a calculator, but now I know. So if this number, this Q, is larger than K, This means that my numerator is too large. That means I have too many products. It will evolve towards reactants. If it's the other way around, the Q is smaller than K, it means that my numerator is not large enough. Therefore, I need more products. So it will evolve towards products. Okay, so notice that we can already predict the outcome even though we do not calculate the exact value of Q.